Up to this point, we've looked at testing a claim about a proportion, testing a claim about a mean, comparing two proportions, and comparing two means. And this test is going to be a test to determine whether or not a frequency distribution follows a specific distribution. So, for example, we could test to see if a dice is fair. If you were to roll a dice, you would expect, if you were to roll a dice a number of times, you would expect almost an equal amount of 1s, 2s, 3s, 4s, 5s, and 6s. So you could test that. We could test to see if the distribution of colors in an M&M sample is the same as the manufacturer claims they are. So for instance, let's say they claim that they make 20% brown ones and 3% yellow ones, and you get the idea. We could test to see if those claims match up to the actual proportions that we find. You could test whether the number of hits a baseball player gets at his next 4 bats follows a binomial distribution. Remember binomial distribution tables that we made a long time ago? Well, you could check against that. So this test is called a chi-square test. It's not symmetric like our other tests. The shape of a chi-square distribution depends on the number of degrees of freedom, just like the student t distribution. However, as the number of degrees of freedom increase, this chi-square distribution becomes more symmetric. The values of chi-square are non-negative. That means that all of our chi-square values are positive, and the symbol for chi-square looks like a funny x squared. So that is the symbol for chi-squared. And chi-square is our test statistic. Remember, we calculated z-scores and compared them. That's one test statistic. We've calculated t-scores. That's another test statistic. And this is chi-squared, another test statistic. To set up a chi-square hypothesis, our null hypothesis is that our random variable follows a certain distribution. So in the instance of dice, we would think that the distribution of each would be 1/6. If we were talking about the M&Ms, we would go with the claim of the manufacturer. And if we were talking about the binomial distribution, we would go with the values of our binomial distribution. Our alternate hypothesis is that the random variable does not follow this distribution. Or in the case of the dice, we could say at least one proportion is different. We can say that actually about all of those 3 examples. So to calculate our test statistic, this is a scary looking formula, and we're going to go through it step by step. But chi-square is the sum of our observed values minus our expected values. We square those, and then we divide that by our expected values. The degrees of freedom are, instead of n-1, it's k-1. And the difference is k is the number of categories we have. It's not our sample size. So in the case of dice, if we were checking to see if a dice was fair, we have 1s, 2s, 3s, 4s, and 5s. Those are our categories, and so there are 6 of those, so our degrees of freedom would be 5. And then the last condition, all of our expected probabilities are greater than 1. Greater than or equal to 1, and no more than 20% of our expected frequencies are less than 5. All right, so let's get to an example. An obstetrician wants to know whether the proportions of babies born on each day of the week are the same. She randomly selects 500 births and obtains the following data. Sunday, there were 46 births. Monday there were 76, Tuesday 83, Wednesday 81, Thursday 81, and Friday 80, and finally on Saturday there were 53. Is there reason to believe that the day on which a child is born does not occur with equal frequency at the 1% significance level? Okay, so let's start off with creating our hypotheses. So our null hypothesis is that all of these proportions are equal, and there are 7 days of the week. So we could say proportion 1 equals proportion 2 equals proportion 3 equals proportion 4 equals proportion 5 equals proportion 6 equals proportion 7. And then our alternate hypothesis would just simply be that at least one of our proportions is different. Because if at least one is different, then that breaks our null hypothesis. And we could say that this equals 1 over 7, or 0.1429 if we want to put it into decimal. Okay, and then we can see that alpha is equal to 0.01. And we can also see that our degrees of freedom are 7 minus 1, which is 6. Now we have to worry about getting our test statistics. So I'm not going to draw a symmetrical curve because chi-square isn't symmetric. But I need a way to find chi-square alpha. That's the value I'm going to be comparing against when I calculate my test statistic. So this is where there is no inverse chi-square on your calculator. You would need to look at a table for this, and that okay. So now that I have my chi-square value, let's go ahead and calculate the values that we're going to need to find our test statistic. We're going to start with our observed values. I'm going to fill in the table with the values that we've observed. That's 46, 76, 83, 81, 81, 80, oops, 2 81s, and then 53. Since we have this table with all this math on it, it would be really nice if the calculator would do some of this grunt work for us. So if we put our observed values in list 1, then we can use the list to do the math. So, and my expected value is, if my proportion were 1 over 7, that's the value I would expect to get if I would expect 1 in 7 births to be on Monday, Tuesday, Wednesday, on each of those days. So I could calculate each one individually, but it's like 500 times 1 over 7. If you round it, it's 71.4. But if I do this and I just put it in the calculator like this in list 2, 500 times 1 over 7, or 500 divided by 7, it'll put in the value for you and it will take care of it so it doesn't round it. So I do that a lot. I find that easier. So that's what the 500 divided by 7 is. It is the same as 500 times 1 over 7. And then it's going to give you a decimal that's bigger than 71.4, but you don't have to type it in and it will take care of the rounding for you. So that goes in list 2. In list 3, I want the observed minus the expected. So I'm just going to go ahead and do go ahead, go up and highlight list 3 and hit enter. The equal sign should flash at that point. And then you can do second 1, which gives you list 1, minus second 2, and you should see list 2. And then you can hit enter, and you will get a table of value. The table will be filled with these values. It should be negative 25.43, 4.57, 11.57, 9.57, 9.57 again, because those two values are the same. And then the last value is negative 18.43. Now I want to take all of these values that are in list 3, and I want to have list 4 square all of them. So I'm going to go above list 4, hit enters, the equals should start flashing. You can do second 3, type in list 3 that way, and then hit the squared button. And that will square all your values for you. And you get some crazy number, 646.61. We have to square the values because chi-square has to be a positive number greater than 1. It means we can't have any negative numbers in our list. So this is 133, not 13. And that last value is 339.61. Okay, and then our final calculation, or one of our final calculations, is we're going to take this value here, our observed minus our expected square, and we're going to divide it by our expected values. So go up and highlight list 5, and then we're going to take list 4 and divide it by list 2. And that gives what each of our categories contributes to the chi-square number. Because you'll see that the chi-square number is the sum, our test statistic is the sum of all these numbers. And then the last one is 4.755. Okay, so we need to find chi-square from this. Chi-square happens when I add all of those values together. So I'm going to take and add 9.053 to 0.293 to 1.875 and so on, all the way down to the bottom of this list. So I'm going to add this together to get my test statistic. And when I do that, I get 19.57. So if I were to compare chi-squared to chi-alpha, it's greater than 16.812. So if I'm just comparing the test statistic, then I would reject the null hypothesis. At least one of our proportions is different. It will be in your textbook. There is in with the other tables a chi-square distribution table. So I've put in a clip of that, and we have 6 degrees of freedom, looking up the degrees of freedom. So I'm going to go to that line, and I'm going to follow it across until I get to 0.01, because that is the area I'm looking for. So chi-square alpha in my case is 16.812. Then you're going to put the observed lists in 1, list 2, just like we did, and then you're going to calculate list 5, not list 3. You're going to use list 5, and then you're going to do a chi-squared test, and that is second stat math, sum L3, chi-squared. Your p-value would be second variables, distribution, chi-squared, CDF, chi-squared to infinity with your degrees of freedom. If you're lucky enough to have a TI-84, you put, in list 1 you put the observed counts, in list 2 you put the expected counts, and then you go to the chi-square. It's chi-square GOF test. That stands for chi-square goodness of fit. So you can't do the chi-square directly with a TI-83, but you can with a TI-84. I can also use a calculator for that. Let me go back and put in our values. Our alpha was 0.01. Our chi-squared alpha was 16.812. And our degrees of freedom were 6. So if you have a TI-83, and I'm going to use a TI-84 to calculate the chi-square goodness of fit, and when I do, that gives me a chi-square value of, let's see, from the calculator, 19.57. And then my p-value, because it also gives you the p-value, is 0.0033. And so if I were to compare, chi-square is greater than my test statistic is greater than chi-square alpha, which means it's in the critical region, and my p-value is also less than alpha. 0.0033 is less than 0.01. So in this case, we would reject our null hypothesis. And that would mean that it appears that at least one proportion is different from the rest. That is my conclusion. At least one proportion is different than the rest. Okay, so the last example today. I need to add another column to this table I see, or row. You know what, I'm going to stick a place in for my total as well. And an urban economist wonders if the distribution of U.S. residents in the United States is different today than it was in 2000. In the year 2000, 19% of the population of the United States resided in the Northeast, 22.9% in the Midwest, 35.6% in the South, and 22.5% in the West, based on the data from the Census Bureau. The economist randomly selects 1,500 households in the U.S. and finds the following counts for 2010. Does the evidence suggest that the distribution has changed since 2000 at 5% significance? All right, well, let's start with our hypothesis. This time, they're not all equal. We have 4 different proportions that we are comparing. And our first proportion from the Northeast, we'll just label it Northeast. The null hypothesis is that it's 19%. And the proportion from the Midwest is 0.229%. And the proportion from the South, very large proportion, is 0.356. And the proportion from the West is 0.225. Wow, I'm really surprised. I thought the Northeast had a lot of people in it. All right, anyways, our alternate hypothesis is that at least one proportion is different from our claim. So now I know that alpha is 0.05. If I look at my degrees of freedom, there are 4 categories: north, east, midwest, south, and west. So my degrees of freedom are 3. And then if I look up on that table, chi-squared with a 5% significance level and 3 degrees of freedom is 7.815. And now I can go ahead and calculate my chi-squared value. So I'm going to do this the long way, but if you want, you can go ahead and put this in list 1, this in list 2, and then just run the chi-square goodness of fit test. So my observed value is 269, 327, 554, and 350. My expected values are 1500 times 0.19. And I would go ahead and put it in the calculator like that so that you get the exact number, not a rounded number. In this case, it's the exact number, but it might not always be. So this one is not an exact number, 343.5. And then 1500 times 0.356 gives me 534. And then the last one, 1500 times 0.225 is a value of 337.5. So list 3, I'm going to go up and highlight, and then I'm going to do list 1 minus list 2, and that gives me negative 16, negative 16.5, 20, and 12.5. And what that represents is that I have 16 less than I expect. I've observed 16 less than I expect in the Northeast, 16 and a half less than I expect in the Midwest, 20 more in the South, and 12 and a half more in the West. All right, and when I square all of those numbers, that would be in list 4, and that's list 3 squared. And then I get 256, 272.25, 400, and 156.25. And then finally, list 5, go up, highlight list 5, hit enter. It'll flash the equal sign, and that's list 4 divided by list 2. I'm going to round these values because I don't feel like writing them all out. And then when I add them up, this column here, I believe I get 2.903. Okay, so that's my chi-squared. Just a quick glance at that looks like I'm going to fail to reject my null hypothesis because it is less than chi-square alpha. Okay, I'm going to go ahead and run this in a calculator and just double check my work. When I run a chi-square goodness of fit test, it is, good. My chi-square value is 2.903. And then my p-value is 0.4068. Okay, so that means we're going to fail to reject. Reason we're failing to reject is that my chi-square value is less than my chi-square alpha, and also my p-value is greater than alpha. So what that means is that it appears that the population distribution has not changed. All right, that's it for today.